In this presentation, we're going to discuss about a couple of miscellaneous topics in C, which we have not discussed so far. First, we're going to discuss command line arguments. Command line arguments are arguments which we pass into the main function. Main int argc, char star argv are the command line arguments. So in this case, argv is an array of strings and argc is the number of elements in the array. So now we will see a demo of a program which utilizes command line arguments and how to manipulate it. So we have a program here which uses command line arguments. So this is the first parameter to main, int argc, and this is the second parameter, argv, which is an array of pointers to characters. So what I'm doing is I'm checking if argc is greater than 1. So I'll explain why this is 1 shortly. And I'm giving an iterative loop here just to print all the strings, different strings from the command line arguments here. So there is an inherent security issue in this program, so I'm not considering that. How do we give the command line arguments? So in the project properties, we have the debugging node. In that, we have something called command line arguments. When you debug the project using Visual Studio, this is how you give. So 1, 2, 3, 4 command line arguments I have given. We'll also execute this program from the console and we'll give another set of command line arguments. Now let's put a breakpoint here and try to debug this. So we have given 4 command line arguments, but we got 5 here. So we'll explain that soon. And we have an array of character. I'm pressing F10. So it has printed the first command line argument. So as you can see, this is a command line argument which we have not passed. So this is the default command line argument to all the application. Absolute path of this exe file or the binary file. So that is the default command line arguments. So the default value of argc is also 1 because all the application got a default command line argument. After that, whatever command lines we have given will come. So I'm printing the loop repeatedly. So the loop got exited. So I can see test, test1, test2 and last. So those are the command line arguments I have given in the project properties debugging settings. Here. Space is the delimiter here. So now let's try to execute this program from the command line itself. So I'm starting a command prompt. So this is where the exe is located. So I'm dragging and dropping it here. I am giving test 100 my cmd arg. So I'm giving 2 command line arguments. So I got those 2 here. And obviously the absolute path of the exe, which is the first default command line argument. Almost all kind of console application use command line arguments. That is one of the most important communication mechanism or user interaction mechanism console application uses. So next topic is functions with variable number of arguments. Printf is a good example of this kind of functions. So normally the declaration is a couple of arguments. After that you have 3 dots. So this 3 dot means that we don't know how many number of arguments comes here. So we use this many functions. So this is a type. These are the functions we use to achieve this functionality. So we're going to see that in a program next. So we have a program here which finds the average of all the arguments passed here. So the last argument we are passing in this function is -1. So if we see a -1, we understand that it's the last argument. So we have 3 integers here. count, which is the number of elements passed, then sum, which is sum of the elements, I, which is an iterator, which is pointing to the first element initially, and we have this VA list, that's a type. Normally it typecasts to a character array or character pointer, so we don't care about the actual type. We use always VA list as it is part of the implementation details of the library. So this is the initialization function. So this function initializes the variable number of arguments. Then here we are extracting one by one until -1. So if we get -1, we don't run this loop. So as per our logic, -1 is the end of the argument. Once that is done, we are ending it here. So this is a function which returns the actual value of the argument to I. We are summing all the i's here and we are increasing the count here. So count and sum is initially 0. So finally we will get the sum and the count here. We divide and give the result back here. So these are the two sample execution. So as I mentioned, -1 is terminator, so this -1 is not part of the summation, so we are not summing -1. So this should return 3, 2 plus 3 plus 4, which is 9 by 3, which is 3, and this should return 32 by 4, which is 8. We'll see this program working in Visual Studio. This is a program. I have copied it to Visual Studio. So I'm going to press F11. I'm going to call VA start to initialize. The value of I is 2. So I've added it to sum. Count has increased 1. Here I'm going to get the next argument which is passed here, which is 3. So after this statement, I should be 3. So now I is 3. I was 2 before. I is 3 now. I is not -1, so I'm executing the loop again. So now I became 4. Now I is -1, so the last one reached. So we are exiting out of the loop. And we are calling end marker to reverse whatever we have done here. Now the sum is 9, count is 3, and we are returning 3. So 3 got printed here. So now we are calling the same function with 4 arguments. In fact, there are 5 arguments, but this -1 is the terminator. So again, same loop. I'm going to press F5. If you want, you can go through the entire looping. So I got 32 here, which is the sum of these 4 elements, and count 4, and I'm exiting out of the program. So I got 8, which is 32 divided by 4. So these are the things we have to remember: VA list, VA start, and VA arc. So we have to initialize the markup first, then we have to call VA end after we have done. So unions, so that's the next topic. Unions looks and behave very similar to structure, but there is a fundamental difference. Suppose there are n elements in a union. Union will allocate memory only for the biggest element. In the case of structure, structure will allocate memory for all the elements plus the padding, etc. In the case of union, union will allocate memory only for the biggest element. So union is mostly used when you want to interpret same memory location in different ways. So this is an example here. So you have a union called test u. Inside that we have 4 elements. One is an integer and 3 character variable. So the size of this union is going to be 4 bytes. So union will allocate memory only for this integer. So these 3 characters share the memory location exactly same as the integer. The access is done exactly same as structure. So we have the same program in Visual Studio here. To see and understand the difference, I'm going to add addresses of all these variables plus its values. So as you can see here, the address of this variable is exactly same. So all these 4 variables are pointing to the same memory location, which also means that if I change any one of them, the other will change. So let's see that. So I'm going to press F10 here. So everything changed. So I made this to 100. So this is also 100. This is also 100. Everything is 100. So it became D. So D is the character equivalent of 100. So now I'm going to make 200. So let's see. So now everything became 200. So integer became 200. So I changed this. So now this became 200. Now if I make 300, this became 44. The reason is I am overrunning this character. So 300 is not fitting into a character. So this became 44. So everything became 44 pretty much. So everything contains the same value. Like that here as well. So this became 144. This became minus. It's the same value pretty much. It's the same memory location, so it contains the same value. So different interpretations. So why do we do that? Before thinking why do we do that, let's see the difference between structure and union. So I'm going to change this keyword to struct. So now if I look at, I can see all these addresses are different. So different memory location, the allocation became different. I'm getting 3 different locations, which means that when I change this, it doesn't affect anyone else other than this. Now this became 100. This became some 52. This may be some other junk. Going to press F10 again. So I can see all these variables got different values. So that is the difference between structure and union. Structure points to different memory location for each element. So these memory locations are different. In the case of union, it is exactly same location. I have added a header file windows.h and I have added a type called large integer just to see a live production union in play. So I'm going to the declaration of that union. So this is here. So this is a union here. So this union contains this many members. So we'll concentrate on this and this. So this structure, so the total memory used by this structure is 64-bit. So 2 32-bit counterparts. The word and long are 32-bit and 164-bit value. In some cases you may want to address this 64-bit large integer as low part and high part. This is the first 32-bit and this is the second 32-bit. In some other case you need to treat it as a single 64-bit value. So whichever the case may be, you can use it because it is a union. So next topic is enum. So enum is pretty much like hash define. So they are a way of defining constants. Also it can auto generate values. So here is a program we have. So we have an enum called day and we have all the days in that. So Sunday I have initialized to 0. So before that, Saturday will become automatically 0. So Monday will become 1, Tuesday will become 2, Wednesday 3, Thursday 4, and Friday 5, like that. So that is the auto generation of value. It is pretty much like hash define. If I execute, I'll get a equal to 5. Type def, we have seen type def as well. So type def is similar to hash define, so related to types, because it's a little bit more intelligent. We have seen in the case of function pointers, type def is very readable, and we use type def in the case of structures. So it is mostly used for giving aliases to complex data types like function pointers, union structures, etc. So this is a syntax. So this is a sample syntax for type def. So wherever you want to use this particular data type, you can use this. So next topic is const. So const is a keyword which we use when we are sure that the value of this particular variable is not going to change. So we have const pointer, pointer to a constant, const pointer to a const. So we will see all of this. So these are the different types of constants here. First one is a variable which is a constant. So int a equal to 10. So it's not a pointer or anything like that. So it's a constant. So a is always 10. So whenever we try to change the value of a, compiler will give this particular error message. The expression must be a modifiable L value. So that is the error we are getting. So this is a pointer to a constant integer. So as you can see, the const is here. So it is pointing to ampersand a. So in this case, you cannot change the value of this pointer. So you can change the pointer address, but you cannot change the value that address is pointing. So if you try to dereference that value and change, you will get an error. The error is again similar. Expression must be a modifiable L value. But you can change the address itself. So here I am changing, so you don't have any red mark here. So there is no error in this particular statement. Next is a constant pointer. So the pointer is constant, but the value is not, which it is pointing to. So you cannot have expression like this. So if you try to change the address, so I'm trying to change the address itself, I have a problem. But I can change the value inside that address, so there is no problem in that. So this is the last statement we have. So in that, both the value and the pointer is constant, so both of these statements doesn't work. So if you do that, you will get this error. If you do that, you will get this particular error. So we cannot do both, because both the value and the pointer is constant. So constant star, const star, ccptr. So next topic is floating point. So floating point, as we know, it's a 32-bit value, and it has a specific format. So in binary, we cannot represent 1.3 or 1.2, something like that. So we use a format to do that. What we're going to do is we're going to explore that format. Total 32-bit. So the first bit is used for the sign, positive or negative. 8-bit is used for something called exponent, which we're going to see shortly. And next 23 bits, so 32 minus 8 plus 1, which is 23, is something called matrica or precision. So I have a float here, my FLT test. So I have assigned a value 13.456. So what we're going to do is we're going to convert the binary value to this particular value. I'm going to start debugging. So I'm going to the memory window to find out the values inside this variable. So ampersand my FLT test. So this is the address of this particular variable. So I have 32 bits here. So these are the bits. So this is something called little endian format, which we're gonna see next. So this is 41 57 for B C7. So it is given in the reverse order of what we read. That's a format called Little Endian. So this is the value, so 32-bit value inside this particular address. So this particular float variable contains this particular 32-bit value. So now what we're going to see is how this particular value is becoming this particular number 13.456. That's what we're going to see. So for that we have to convert this into binary first. So I have started the calculator. I'm switching to dword and hex, and I'm copying this and I'm pasting it here. Now I'm going to bin to convert it into binary. So Control A, Control C, Control V. This is the binary equivalent of this particular number. So I'm going to add a 0 here. So this 0 is the first bit. So this is a 32-bit number. 4 into 8, 32. So this bit is 0, which means that this is a positive number. So first bit is the sign bit. So number is positive. So next 8 bit. So next 8 bit. So this is the next 8 bit. This 8 bit is called exponent. Let's see what is exponent. So exponent is a number from which we should subtract 127. So we have to subtract 127. So next 8 bit minus 127. That is the operation we're gonna do next. So this 127 is decimal. So we are going to take the next 8 bits, coming here, Control V. So this is the next 8 bits, moving to decimal and subtracting 127. So we got 3. So what to do with this 3? For that we have to consider the next 23 bits. So I'm copying it here. Now what I'm going to do is I'm going to do a 1 point here. So I have added a 1 point in front of the next 23 bits. Now what I'm going to do is I'm going to shift this dot 3 digits. So that is where this 3 comes. So I have shifted 3 digits. So this number is the binary representation of this number. So let's prove that. So I'm going to convert this number to decimal. 1101. So that is 13. Now to convert this number which start with a dot to decimal, I'm going to use the conventional technique. This was supposed to be 0.5 or 1 by 2. So this is 1 by 2 raised to 2 or 1 by 4, which is 0.25. So I'm switching the calculator to normal mode. So 1 by 4 plus is 1 by 8, 1 by 8 plus 1 by 16 So if you look at, as we add, this value get close to this 456 as we continue adding. So I added 1 by 16. I don't have 1 by 32, so now I'm going to add 1 by 64 plus 1 by 64. Now I don't have 128, I don't have 256, I have 512. So this is 512. 1 by 512. So I got 455. I'm supposed to get 456. So 512, I don't have 1024, I have 2048. 1 by 2048. So it's getting very close. So if you continue adding like this, you will get more and more close to this particular value. So you can continue doing that until you get more closer value. So I'm stopping here. All my motive is to show you how this calculation works. So once again I'm repeating. So this is the binary value which is stored in this particular variable. So this is the exact binary representation. So this is the hex representation we got from the memory window. The first bit is sign bit. We found out that that bit is 0. So this number is positive. So next 8 bit, this 8 bit converts to 130. We subtracted 127 from that and we got 3. What did we do with that 3? So we took the next 23 bit, added a 1 point in front of it and shifted that point 3 times right. That's why we got this. So this number is the binary equivalent of this number. So this is how the floating point is represented in computers. So there are other formats of floating point as well, but in most cases we use this particular format these days. So now let's go back to the presentation. So one of the point with floating point numbers is some of the floating point numbers cannot be represented correctly in memory. For example, let's consider the number 1 by 3. So 1 by 3. So we cannot represent 1 by 3 in decimal. You will get 0.333 infinitely. Like that, some of these decimal numbers cannot be represented completely in 2 base numerals or ones and zeros. You need to have infinite ones and zeros, but computer memory is always limited. This problem we have to take care when we deal with floating pointers in our programs. So this is an example which is given to demonstrate this problem. So this is taken from MSDN again. We are going to discuss the floating point precision and some problems around it. First, let's try to understand what this program is doing. So we have 3 floating point numbers here, A, B and C. We are assigning A to this particular value, B to this value, and adding A plus B. So we know the result. So if you do that math, your result is this particular value. We are expecting this condition to be true always. But in the case of computer, in some cases, computer may not be able to represent this value exactly as it is because of the reason I mentioned before. Computer has to represent this number in binary. In the previous format we have seen, computer may or may not represent this number correctly with infinite precision because this is a 10 base numeral and we are trying to express this in 2 base numerals. So maybe in the computer memory it is represented as 2.46 7,999, which is very near to this particular number, but it's not equal to this number. So there is a good chance that this particular statement may fail because C is not equal to 2.468. it is always recommended that you never compare floating point numbers with equal to operator. Then what we should do? We should do something like this. Let's try to understand what this macro is doing. So this macro is doing the difference between these two values are within this limit. This is something we are calling tolerance. So if the difference is less than this tolerance, we are going to consider it equal. So that's what we are doing here. So v minus epsilon less than x and x less than v plus epsilon. So this is very much similar to equating it within the limit of this tolerance. So it depends on your CPU precision. You should adjust the tolerance. Some of the CPU is very precise, some of the CPU is less precise. So the bottom line is never use comparison or never use equal to operator in the case of floating pointer, because computer may or may not be able to represent a floating point number to the absolute precision. So now let's try to execute this program. So here is the same program in Visual Studio. As I was saying, the value inside C is 2.467, after that 49. So we are expecting this particular value, but we got a very close value, but not this value. So this check is going to fail. So not equal. So we got printed not equal. The fix for this bug. So this is a wrong coding. So this is a wrong way of doing things. So I'm going to comment out that statement and going to use this statement inside. So now I'm getting equal because it is close to C within this tolerance value. So this is very important. If you're dealing with floating point, it's very easy to make this mistake. It's not a best practice, it's a rule which we have to follow. Never compare floating points. The next and the last topic is endianness. So endianness is always related to how we store data in the memory. So there are two types of endianness majorly: big endian and little endian. So Intel CPUs uses little endian. So there are processor which uses big endian as well. Big endian means that the higher address has the least significant byte. So if you have an integer or a word size variable, the least significant byte of that integer will be in the higher address when the CPU stores it in the memory. Little endian is just the opposite. Lower address has the least significant byte. Intel uses a little endian, which we're gonna see in Visual Studio right now. So we have a very simple application here. I have a variable test here, which I have initialized to this particular number 0x12345678. It's a hex number. My breakpoint is currently hit here, which means that test contains this particular value at the moment. Now I'm going to look at memory. So ampersand test. So I got this particular value. So what I'm going to do is to see each address. I'm going to make this 1. So 1 byte at a time. So as you can see, this is the lower address. This is the higher address. So CC, CD, CE, CF increasing when we come down. So 78563412. So this is the variable. So 1 2 3 4 5 6 7 8. This is the least significant byte that is in the lowest address. So this is the highest significant byte which is in the higher address. So if it was big endian scheme, this would have been 12 3 4 5, 6, 7, 8. Just the opposite. Now let's go back to the slides. So we have looked at big endian and little endian. So both have some advantages and disadvantages. I'm not going to discuss it here. So being said that, we are almost done. Thank you very much.